Hi everyone, thanks for checking out this video. Um, so in this video, I'm going to talk about uh, on parity decision trees for Fourier-sparse Boolean functions. Uh, this is joint work with Swagato Sanyal, who's at IIT Kharagpur. This work done while I was a postdoc at Georgetown University, and I'm currently at CWI Amsterdam. Okay. So in the first part of the talk, I'll try to explain to you all the terms in this title here. So I'll be in the first part of that, I'll explain what Fourier-sparse Boolean functions are. And then after that, I'll tell you what parity decision trees are. And right after that, I should be able to give you some motivation as to why people care about parity decision trees. In particular, why would one care about parity decision trees for Fourier-sparse Boolean functions? And then I'll give you an idea about how we want to construct efficient parity decision trees for Fourier-sparse Boolean functions. And, and after which I'll state our main theorems. And then I'll summarize in the end with a summary and one open question. All right. So in case you already know some basic Fourier analysis of Boolean functions, you can skip this part. But otherwise, here it is. So we're going to consider the space of functions from F2 to the n to R as a real vector space where addition is pointwise addition, scalar multiplication is pointwise scalar multiplication with that scalar. So this space is a vector space, and we're going to equip it with the following inner product. Conceptually, what does this inner product do? Between functions f and g, it computes the correlation between f and g in some sense. More formally, it's inner product between f and g is defined to be summation fx gx scaled by a factor of 2 to the n. Now the goal is I'm going to tell you, I'm going to construct an orthonormal basis for V under this inner product. One may verify that this is an inner product. I'm not doing it in the slides. It's fairly easy to check this. So for each alpha, which is a vector in F2 to the n, so there are 2 to the n such possible vectors, I'm going to define a function chi alpha, which I'm going to refer to as the character corresponding to alpha, or also occasionally interchangeably the parity corresponding to alpha. So for each alpha, define its associated character or parity to be the following function. So look at all the coordinates where alpha is 1, and on input x, compute the parity of those coordinates. So that's exactly what this function is doing. It's outputting a 0 or 1 value, and then convert that to -1, 1. So one can check that there are 2 to the n such functions, and the dimension of this space is indeed 2 to the n. So you can check that this set of all chi alpha, the set of these 2 to the n functions, forms an orthonormal basis for this vector space that I defined. Good. Thus, any function f from f2 to the n to r has a unique representation as a linear combination of these parities. So any f can be represented as summation f hat alpha chi alpha, and the coefficients f hat alpha are called the Fourier coefficients of f. Great. So we're interested in Boolean functions. When I say Boolean, throughout this talk, I'm going to mean that the range is Boolean. The range is -1 or 1 value. So denote the Fourier support of f to be the set of those characters whose set of non-zero Fourier coefficients, basically. Set of characters whose Fourier non-coefficients are 0. Fourier coefficients are non-zero, I'm sorry. And the Fourier sparsity of f, we're going to denote it throughout this talk by k. Note that I'm dropping the dependence on f here, but the function is going to be clear from context. The Fourier sparsity of f is the number of non-zero Fourier coefficients in the expansion of f. For example, if you were to compute the Fourier sparsity of the parity function on n variables, that's going to be 1. If you were to compute the Fourier sparsity of the AND function on n variables, that's going to be 2 to the n. There's a natural equivalence between elements of f2 to the n and subsets of n, which I'll also be using throughout this talk. An n-bit string in f2 to the n has an analogous characteristic set, which is a subset of n, which corresponds to all coordinates where alpha I is 1. Great. So now I told you about Fourier analysis of Boolean functions. What does it mean for a function to be K Fourier sparse? So I'll be dropping the word Fourier when I talk about Fourier sparse. I'll just refer to sparsity rather than Fourier sparsity, just for ease of notation for this talk. So next, I'll tell you about parity decision trees. This is a model of computation to compute a Boolean function. Let me try to describe via an example how a parity decision tree computes a function. So in this figure here, this is a parity decision tree. If you're familiar with the notion of decision trees, it's exactly the same, except queries that are made are parities rather than variables. So it's a generalization of decision trees. If you're not familiar with decision trees, let me try to explain via this example. So this parity decision tree takes as input a 4-bit string and outputs a value in 1 comma minus 1 the following way. First, it queries x1 xor x2. If it's 0, go to the left subtree. If it's 1, go to the right subtree. And iteratively keep doing this until you hit a leaf. And if you hit a leaf, then output the value at that leaf. So for example, if I query x1 xor x2, I get a 0. Query x1 xor x3, get a 0. Output the value 1. So this parity decision tree computes a particular Boolean function on 4 input bits. And the parity decision tree complexity of a Boolean function f is the minimum depth of a parity decision tree that computes f. So depth is the measure of our interest. Great. So now I've told you what Fourier-sparse Boolean functions are, what parity decision trees are, what that model of computation is. Next, let me talk a little bit about motivation. Why do we even care about parity decision trees for sparse Boolean functions? First of all, what's a trivial upper bound? Suppose the Fourier sparsity of a function f is k. So write out its Fourier expansion, f equal to summation f at alpha chi alpha. Now you can just query all the values of the chi alpha. So you just query all the parities that are present in the Fourier support. And the moment you have the answers to all of these, just plug it into the Fourier expansion and you just get out the value of f directly. So a trivial upper bound on the parity decision tree complexity of f is its Fourier sparsity. Now I'm going to tell you about why, like a few bullets about why we really want to improve upon this. So define this XOR function. This plays a crucial. I mean, XOR functions are important in the context of communication complexity. For example, I'm not going to define the model formally here, but very roughly imagine that there are two parties, Alice and Bob. Alice holds an n-bit string x1 to xn. Bob holds an n-bit string y1 to yn. And they wish to compute the value of f on the bitwise XOR of their inputs. And they wish to minimize the amount of communication amongst themselves to do this. Trivial solution is Alice can just send all of her inputs to Bob and Bob can compute. So that's n bits of communication, and ideally we want to get as little communication as possible. So if we have an efficient parity decision tree for f, this immediately yields an efficient communication protocol for f of xor. It's fairly straightforward to see. I'll not go over the proof now. It's not that hard. And the other direction, recently Hatami, Hosseini, and Lovett, they proved that given an efficient communication protocol for f of xor, you can actually extract an efficient parity decision tree for f. And using known results about the rank of communication matrices corresponding to XOR functions, which is exactly equal to the Fourier sparsity of f. So the parity decision tree less than equal to complexity of f being polylog its Fourier sparsity is equivalent to the log rank conjecture for XOR functions. So if you don't follow any of this slide, feel free to ignore it. There is just some motivation for people who are already doing some research in related areas. And the best progress towards improving upon this trivial upper bound of PDT less than equal to K. So note that ideally, we would want to show that PDT is polylog K. Best progress towards this is a result due to Sang, Wong, Xie, and Zhang, which shows that parity decision tree complexity of F is at most square root of its Fourier sparsity. So note that we're still very far away from this goal, polylog K. And in fact, now I'll tell you a little bit about the proof of Sang et al. And there was also a result of Spilka, Thale, and Volk that came out around the same time, which had quantitatively weaker results. But the proof ideas were extremely similar. Great. So now the goal is I'm going to tell you how did Sang et al. Construct, beat this trivial bound. How did they construct the square root K depth parity decision tree for F? Here's the idea. Suppose there's a small set of parities, first of all. Suppose there's order square root K parities, such that when you query these parities and you get a particular fixed set of answers to it, then the function becomes constant. What does that mean in this picture? Suppose the set of parities is x1, xor, x2, and x1, xor, x3. And if the answers were 0, 0, we know that f is a constant. Suppose there exists such a leaf. Now, this is where the novelty of their work is. I'm not going to explain about how they obtain such a leaf. If there does exist such a leaf, then I claim that on all other answers to this same parity queries, the sparsity of f is going to drop by a multiplicative factor of at least 2. I'll tell you a little bit about the sketch on the next slide, and I also hope to tell you, give you an indication as to where we deviate from their proof, and uh, yeah. So just looking ahead, sorry, I should have mentioned this. Looking ahead, we are going to reprove this result. Parity decision tree is at most order square root K. And we're also going to give a conditional improvement. And I'll tell you about the conditions later. And our reproof, hopefully I'll be able to tell you what the key differences are with our work and the works of Sang et al. And Spilka et al. On the next slide. So suppose you believe this claim for now, then just run the same procedure on each leaf. So the sparsity of the function here is already 1 because it's a constant. And the Fourier sparsity on each other leaf by this claim is going to be at most K by 2. And the depth of this tree is square root of K. So if you just run the same procedure at each leaf until you reach a constant at every single leaf of the whole tree, the depth of the total tree is going to have this recurrence, which is easily seen to be order of square root K. And again, giving you a bit of spoiler for the future, our procedure is going to follow a same approach, being we're going to find a square root K depth set of parities such that every leaf has sparsity at most K by 2. We're going to bypass this step that says that there is one leaf where f is a constant. And that's the key place where our procedure differs from these works. So let's consider a toy case. So on this slide, I'm trying to sketch why does this claim hold true. Suppose there is a leaf where f is a constant, then all other answers to the same parity queries will be such that the restricted function f on those leaves, the sparsity has dropped by a factor of 2 from the original sparsity, at least 2. Let's consider a toy case. Suppose there's a function f which is non-constant. In particular, without loss of generality, let's say it has this term appearing in its Fourier expansion. And say we fix x1 equal to 1 and it makes it a constant. What does that do to the Fourier expansion of f, fixing x1 equal to 1? Let's see. In general, this fixing x1 equal to 1 would be fixing a set of parities to a certain set of values. But this is just a toy case for illustration. So fixing x1 equal to 1 means this coefficient, this whole term collapses to minus x1, minus of a12 minus 1 to the x2. So here a12 is the Fourier coefficient of this parity. But now we know that f when restricted to x1 equal to 1 is a constant. So what does that mean? This term cannot survive in the Fourier expansion of the restricted function. So it has to cancel with something else. So there must be some other term that gives you or a sum of other terms, which also when you plug in the value x1 equal to 1 gives you terms of the form some constants time minus 1 to the x2. Okay. So in general, this is the statement. If you have a set of characters, in this case the character was just x1, and if each beta is identified with some other delta. So if this might be a lot to take in, but I'll just give you an example in a line. Basically, if there are two parities which get identified under this set of characters. So in this example, the parity minus 1 to the x2 on fixing x1 to equal to 1 would remain minus 1 to the x2. But also minus 1 to the x1 plus x2 would also be a constant times minus 1 to the x2. So x2 and x1 plus x2 get identified under x1. And the Fourier sparsity is going to drop by a factor of 2. Because of this identification, these two terms which were contributing two terms to the sparsity in f are now contributing just one term. And that's the idea. Note that we didn't really need this function to be a constant. If we could on a particular restriction, if we could just show that there's a bunch of there's a small set G of characters under which a lot of characters in the Fourier expansion of f identify with each other, or let's say all of the characters identify with some other character. So what does that mean? The sparsity is going to drop by a factor of at least 2. So here's the example. If your set of characters was, instead of just x1, if it was corresponding to x1 plus x2 and x2, then note that these terms are going to be identified with each other. They might not necessarily cancel out, but what was contributing 3 terms to the original Fourier sparsity is now contributing just 1. Okay, and these were contributing 2 terms, and now they're just contributing 1. In general, the number of under braces in this case, let's call it the bucket complexity of f with respect to the set of characters G. Great. So now let's take a small detour. Let me tell you about. Our goal right now is, given a Boolean function f, how can we come up with a set of characters G such that the bucket complexity is small. The bucket complexity is basically the number of, is an upper bound on the Fourier sparsity of the restricted function under any restriction. Yeah. So note that any restriction of these parities is going to make the Fourier sparsity in this case at most 2. So Parseval's identity is take any Boolean function f, consider the f square, which is the pointwise product of f and f, and write out this expression. So f square on the one hand is equal to the constant function 1, since fx times fx is always equal to 1 if the range is minus 1, 1. And on the other hand, we write out this expansion times itself. And notice there's a bunch of cross terms. So there are terms of the form chi gamma, and what are their coefficients is exactly alpha 1, alpha 2, f at alpha 1, f at alpha 2, such that chi of alpha 1 plus alpha 2. So I didn't tell you this earlier, but chi alpha 1 times chi alpha 2, it can be verified to be chi of alpha 1 plus alpha 2 fairly easily. So this is exactly the expansion that comes out. And comparing the constant terms on these two sides, you get f at summation f at alpha square equal to 1. And comparing the non-constant terms, we get this identity. Okay. And this is what we're going to refer to as Titsworth's conditions, and these are going to be important for the remaining few minutes of the talk. So what does this mean? Suppose there was an alpha 1, alpha 2 which are not equal in the support of f. So f hat alpha 1 times f hat alpha 2 is non-zero, right? But this condition says there must be another pair beta 1 beta 2 such that f at beta 1 f at beta 2 is non-zero, and beta 1 plus beta 2 is the sum of alpha 1 plus alpha 2, because this sum has to be equal to 0 for all gamma non-zero. Great. This gives this induces a natural equivalence relation on um, pairs in S choose 2, where S denotes the Fourier support, where the equivalence relation is two pairs are equivalent if their sums are equal. And let's denote by d gamma the set of all pairs corresponding whose sum is gamma. And just from this previous expression here that I showed you, and the small discussion that I had, we conclude Dirichlet's proposition, which is for any Boolean function and for all pairs of parities in the Fourier support, there must exist another pair of parities whose sums are equal. So in other words, the size of every equivalence class is at least 2. Okay. Now our main theorems here. Our first main theorem is I'm going to tell you that any Boolean function has small bucket complexity with respect to a random set of parities. So pick a random set of square root k parities. Just interpret these first two lines as that. Then with high probability, the bucket complexity of f with respect to these set of parities is, let's say, at most a half of k. Some technicalities, but yeah. And as a corollary, as I told you earlier about why our proof is deviating from that of Sang et al. And Spilka et al., the parity decision tree complexity turns out to be order square root k. And let me skip the proof sketch for the interest of time, but I'm lying a bit in this second phase here. But if you're interested, feel free to pause and take a look at this. And in particular, we show a conditional improvement, which is if our function is such that, suppose all functions are such that the sizes of the equivalence classes are extremely large for a large fraction of pairs. So imagine delta equal to 1 for a moment here. So suppose every equivalence class has size poly k. Right now, all that we know is that each equivalence class has size 2. Yeah. So if each equivalence class is size poly k, then we can show that we just modify the proof on the previous slide, and we can show that parity decision tree complexity of f is k to the 1 minus L by 2, which improves polynomially over the best known result of square root k. And this in particular recovers the result that I showed you on the previous slide, except up to log factors. Great. So the next question we ask is, are Dirichlet's conditions tight? Can we even hope to expect this, that almost all or all Boolean all equivalence classes are of large size? Okay, because there's no evidence so far. You might be wondering, why am I making such a ridiculous claim if there's no evidence? So for example, the first question we can ask is there a Boolean function for which every equivalence class is size exactly equal to 2? And to our knowledge, this was not known before this work. We say that no. So this is, a speck of evidence towards hoping that every equivalence class is a poly size. And we show that this is not true. In particular, we show the following theorem. For every alpha, there must exist another beta for which that equivalence class has size at least 3. And we have a corresponding tightness result as well. And let me not again tell you about the proof sketch, but it involves Dirichlet's proposition, granularity of Fourier coefficients, and Parseval's identity. So it's fairly first principled proof, this one. Great. And in summary, we reprove a result from Sang et al. And we show that a naive sampling of parity suffices. And we don't need to force the function to a constant after each phase. We just need the bucket complexity to be small. And we give a conditional improvement upon this. And and the conjecture is every Boolean function is delta half minus little o1 of little o1 folding. This also has consequences in towards improvement of the log rank conjecture for XOR functions. And all right, thank you.